Okay, I see. Sorry about that. I see that you guys were not hearing me. Okay, very good. I'm sorry about that. I did not turn your mic. I believe my mic was off. Okay, now let me start all over again. A good Sunday evening to all of you. And I do want to welcome everybody to the second online review session in organic chemistry. For today's session, we are going to start with question 4, which is taken from a previous second exam that was given in the fall of 2012. I do also want to let you know that questions 3, 8, 12, 17, and 19 will not be covered tonight. I also want to let you know that questions 1 and 2 were already covered in class, so we are not going to cover those 2 questions also. Okay, but before I start the session, let me go ahead and acknowledge those of you who have already joined us. See, Masha K. Hutchinson, Avonia Rickson, Brittany Galloway, Shante Smith, Danutika Gelling, Erin Walters, Ganesh Mohan, Jasmine, Jerisa Jackson, Jerome White, Gillian Pelling, Jodwina Gaskin, Kayla Boudreau, Kiara Wallace, Kiara Price, Lauren Kibet, Makiva Walker, Mohammed Fahad, Nashima Macbeth, Nolan English, Raquel Abraham, Robin Onoha, Ronel, Sachin Vaskiran, Sean Taylor, Sipora Christopher, and Victoria Faulkner. Okay, you are all welcome. Okay, Danutika Gedin, can you go ahead and read this question for us? Question number 4.
Which of the following reagents will give an aldehyde when reacted with 2-methyl-2-butene?
Okay, thank you. I'm very good. Okay, so this question here, what this question is testing your knowledge of nomenclature. It is also testing your knowledge of the reagents. Now, before we start the session today, let me make it very clear to all of you. You must know what the reagents do. You must know what the reagents do. I guarantee you, if you know what all of the reagents do, you will not have any problem with organic chemistry. Okay. So let us approach this question here. The first part of this question, you need to know the structure of this molecule. So this is 2-methyl-2-butene. Let us write the structure here. Two-methyl-2-butene. Okay, can anybody tell me what is the longest carbon chain in this molecule? What is the longest carbon chain in this molecule? What is the parent name for this molecule? Just give me the number. Let's see here. Okay, 4, 4. Great. Okay, very good. Okay, so this is carbon 1, 2, 3, and 4. Okay. Now, the next part of this question is to know what each one of these reagents will do. So let me help you out here. This here, ozone followed by zinc and acid Does anybody know what that would do? Can you pick up the mic or send me through the information through the chat window? Ozone followed by zinc and acid. Okay. Okay, very good. Okay, so what that will do is form carbonyl. Okay, very good. Form carbonyl. Okay. I am going to be very specific here. Ozone followed by zinc and acid, what it will do is to cleave a carbon-carbon double bond to give ketone and aldehyde. To give ketone and aldehyde. Okay, we need to be very clear as to what each one of these reagents will do. Now let us take a look at the second one. Potassium permanganate with aqueous sulfuric acid, sometimes we refer to as dilute acid. What does it do? Anybody know? What that would do is to cleave a carbon-carbon double bond to give ketone or carboxylic acid. To give ketone or carboxylic acid. About C, this here, osmium tetroxide. What does it do? What it will do is to add two OHs, two hydroxy groups, across a carbon-carbon double bond such that the two OHs will be cis to each other. In other words, this reagent here, osmium tetroxide, is what we call a cis addition reagent. Cis addition reagent. Or sometimes instead of cis, we say syn. That is the same thing. Now, finally, D. The reason I do want to take some time to explain this to all of you, because this is most important. If you miss this, there is nothing you can do with organic chemistry. Okay, for D, what does this reagent do? M-chloroperbenzoic acid, sometimes we abbreviate as MCPBA. Okay, forms an epoxide. Exactly. Very good. Okay, very good. All of you got this right. So, but for the benefit of some of you, let me go ahead and write this out. This reagent here will add oxygen to a carbon-carbon double bond to give and epoxide. Okay. Now that we've given you all of those information, this is the question here. Which of the following reagents will give an aldehyde when reacted with 2-methyl-2-butene? That is this molecule here. Okay, so what is the answer here? Let me see. A, very good. Excellent, excellent. Okay, very good. Okay, you could see now, once you know what those reagents do, this kind of questions become very, very easy. So the answer here is A. The answer is A. Because if you take a look at this, if you take a look at this molecule here, and we react with step 1, ozone, and step 2, zinc followed by acid, you clip this here, and this carbon here, let me number the carbon. This is carbon 1, 2, 3, and 4. So carbon number 2 becomes the carbonyl of a ketone because it does not have an hydrogen attached to it. And carbon number 3 becomes the carbonyl of an aldehyde because it has an hydrogen attached to it. So therefore, you are going to get this. You get that compound, and then you also get this is the ketone, and you also get the aldehyde. Get the aldehyde, and you also get the ketone. Now, if that is clear to all of you, give me a happy face. If that is clear to all of you, give me a happy face. Okay, excellent, excellent, excellent. Very good. Okay. I know some of you are writing this down, so I will give you a few seconds to finish your writing, because I do want to ask you additional question on this particular question here. Okay, very good. Now, as I say, I want to spend some time on this question because it is a very important question, because it allows you to get to know what these reagents do. Now, supposing I ask you, based on the definition that we gave you earlier on what these reagents do, supposing I ask you, let us focus on reagent number 2. Okay, and this is the compound that we have here. Okay, I use now reagent number 2, which is potassium permanganate in sulfuric acid. What will be the product? What will be the product? Anybody has an idea? Will it be, just tell me whether it's going to be ketone, carboxylic acid, or aldehyde. And then when you do that, tell me which carbon will become the ketone or carboxylic acid, and which carbon will become, yes, or which carbon will become carboxylic acid or ketone. Let's see here. Okay, let's see. ketone and carboxylic acid, ketone and a ketone. Okay, very good, very good. I think most of you got it right. Said ketone for carbon 2, very good. So therefore, this will be your answer here. The carbon 2 becomes the carbonyl of a ketone, and then the carbon 3 will become the carbonyl of a carboxylic acid. Okay? Because anytime you have an hydrogen attached to the carbon of a carbon-carbon double bond, and you use this reagent here, you get carboxylic acid. And that carbon that does not contain an hydrogen, for example, this here, becomes the carbonyl, the carbon of a carbonyl for a ketone, which is this here. This is carboxylic acid. Okay, so you guys got the idea. So let us move on. Okay, let's see here. Masha K. Hutchinson, can you read this question for us?
What products would you expect from the following reactions?
Okay, very good, and thank you. It says, what product would you expect from the following reaction? Once again, this goes back to you must know your reagents. Okay, so what is the answer to this question? By the way, you should have here step 1, step 2, sodium, hydrogen sulfide. That is out. Okay. So what is the answer here? D. Everybody got D right. Very good. So the answer here is D. Okay? Because this reagent here, just as we told you in the last question, what it does is to add, in this case, you can see here, 2 hydroxy groups across the carbon-carbon double bond, which is this here, such that the 2 hydroxy group will be on the same side of the molecule. Okay? So therefore, we say this is a syn addition reagent. Okay? Very good. Is that clear to all of you? Okay, no question. Okay, very good. Let's go to the next one. Okay. Kiara Price, can you read this for us, number 6?
Supply the missing starting material or product for the following reactions. No mechanism required.
Okay, thank you. Very good. Okay, what this question wants you to do, of course, is to supply the missing starting material or product for the following reactions. Now, once again, this is a question of knowing your reagents. So I need to keep saying this. You must know your reagents. Okay, so let us do this. This carbon-carbon double bond in cyclohexene will react with this reagent here. What product do you expect to get? Anybody? Is it ketones, carboxylic acid, aldehyde, or whatever? Excellent, excellent. 2 carboxylic acid. Excellent. You must know that. Okay? Because what you have here, there is hydrogen here, and there is hydrogen here. So when you cleave, somebody have their mic on. Oh, okay, I'll turn your mic on. Okay. So when you cleave this carbon becomes the carbonyl of a carboxylic acid, and this other carbon here also becomes the carbonyl of a carboxylic acid, because each one of them is attached to hydrogen. Okay? So therefore, the product will be here. If you see here, let me number this carbon here. This is carbon 1, carbon 2, carbon 3, 4, carbon 5, and carbon 6. Okay, and that is right here. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Okay. Okay, so about this one here, I believe we did this in class on Thursday. Okay, what type of reaction is this? What does this reagent do? What does this reagent do? Okay, this is an example. This one here is an example of electrophilic addition reaction. To carbon-carbon double bond. To carbon-carbon double bond. Following Markovnikov rule. Okay, in Markovnikov rule, it says whenever you have a carbon-carbon double bond, if you add an hydrogen atom and a nucleophile, in this case you have hydrogen and the chlorine will be your nucleophile, the hydrogen will add to the carbon that contains more hydrogen. So this is a case of the rich get richer. So the hydrogen will attach to the carbon that contains more hydrogen, and the nucleophile will attach itself to the carbon that contains less hydrogen. So therefore, the product will be here. Hydrogen goes here. Keep in mind there was already an hydrogen there. And then chlorine goes here. And you have this metal here. Okay. So that is what you get in this type of reaction. So therefore, what will be the answer to this? What is the starting material here? What is the starting material? If you look at this, we have to say that the double bond has to be here between this carbon and this carbon. Let me go ahead and number the carbons. If we say this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. Okay? Therefore, we will say the starting material will be, one of the possibilities will be this. That is one of the possibilities. In other words, we have, this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. So in this case, if this hydrogen comes here, following Markovnikov's rule, the chlorine will go here. Okay, so this is a possibility. I know some of you will say, well, why doesn't the hydrogen go here to carbon number 4, and then chlorine comes here? That is also possible. But that is not what they tell us to explain here. So the point is, this is capable of giving you this product right here. Now, the other possibility is, if the carbon-carbon double bond is between carbon 4 and 5, okay, and that will be this here. In this case, this hydrogen here will come to carbon number 5, which is this here, and the chlorine will go to carbon number 4, which is the product they want us to explain. Now, if this is clear to all of you, give me a happy face. Okay, very good, very good. Okay, so let me take this out. Now for this here, let me just go ahead and give this to you. No, we did not actually spend too much time on this, but we did this long time ago. If you have hydrogen and what we call a catalyst, okay, what this reagent does is to add 2 hydrogen atoms across the carbon-carbon double bond. By the way, somebody is asking here, the last question this year, do you have to give the 2 starting materials? Yes. In order for you to get the complete, the full credit, you need to give both of the possibilities for this question here. Okay. What this reagent does is to add 2 hydrogen atoms across the carbon-carbon double bond in such a way that those 2 hydrogen atoms will be cis to each other. In other words, this is a cis addition reagent. For example, if I have this, and I use this reagent here, hydrogen and palladium. Sometimes we may use, instead of palladium, we may use platinum. Okay? Okay, hydrogen and palladium, what does it do? It will add 2 hydrogen atoms across the carbon-carbon double bond such that those 2 hydrogen atoms will be cis to each other. Okay, we know the metal is still here. Okay, so therefore, in this particular instance here, this here, what does it do? This here will give us, we'll add hydrogen here and hydrogen here, okay? Okay, that is the product. Okay, let us do the last one. Okay, we did this in class also. Let me go ahead and number these carbons here. I say this is carbon 1 and this is carbon 2. Okay, what kind of reaction is this? What is going to happen here? What does this reagent do? Can you tell me? Where would the hydrogen go? And where would the bromine go? Which carbon will hydrogen attach to? Okay. Am I getting response from you guys here? Let us see here. Okay. So the hydrogen goes to carbon number 1 and bromine to carbon number 2. Excellent. This is another example of a Markovnikov addition. Okay? So therefore, the product will be the hydrogen goes here. Keep in mind, you already have one hydrogen here anyway, and then the bromine goes here. There was hydrogen here already. Okay, so we have finished question number 6. Okay, let us go to the next one. Question number 7. Okay, Erin Walters, can you go ahead and read this for us? Number 7.
Provide structures for the following: A, 6-isopropyl 1-methylcyclohexene, and B, 3E5Z 2,6-dimethyl 1,3,5,7-octatetraene.
Okay, very good, and thank you. Okay, so this is a straight, this is a question just testing your knowledge of nomenclature. So this is just a nomenclature problem. Okay, let us see here. We have cyclohexene. That is the base name. Actually, here, this hyphen should not be here. So this is an error. This hyphen should not be here. Okay? Please note that. Okay, so we have 6-isopropyl 1-methyl cyclohexene. So the base name is cyclohexene. So we have this. Okay, cyclohexene, we have double bond here. We say 1-methyl. Okay, now we then number the carbon chain. Say this is carbon 1, carbon 2, carbon 3, 4, 5, and carbon 6. So therefore, the isopropyl group must be on this carbon. And isopropyl is this here. Okay? Is that clear to all of you? If it is, give me a happy face. Okay, very good. Now let us do B. 3E5Z 2,6-dimethyl 1,3,5,7-octatetraene. So what this tells us, the base name must have 8 carbon atoms, and then you also have 4 carbon-carbon double bond in the base name, and those carbon-carbon double bonds are in positions 1, 3, 5, and 7. And then you have branches in positions 2 and 6. Now we also notice here that the stereochemistry that we have here is only in positions 3 and 5 of the double bonds. So what that tells you is that you do not have stereochemistry in position 1 and 7. Oh, okay, with that information in hand, let us see. Let's start with position 1. We assume this is carbon-carbon double bond in position 1, since there is no branch here. Okay, then we have this here. This is 1, 2. Then in position 3, we have another double bond. And they tell us that will be that will be E. So therefore, I'm going to place my hydrogen here in order to make that E. And then in position 3, we have position 2. Sorry about that. In position 2, 1, 2, we have a methyl, position 2. Okay. So therefore, we have hydrogen here. Okay, that is 1, 2, 3, 4. And then position 5, another double bond. And they tell us that will also be E, and that is Z. Okay, that is Z. So therefore, what do? I have this here, this here, this here, and 1, 2, 3, 4, 5, 6. Okay. On the 6th position, you have a methyl. Okay, that means on this here, we have hydrogen. And then here we have, this is carbon number 7. Okay, that means we have this, and then that also means we have this here. Okay, let us see, let us number them. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Do we have everything in place? We have 2, 6 dimethyl. Okay. In the 2 position, we have a methyl. In the 6th position, we have another methyl. Those are your branches. Okay. Now the stereochemistry in the 3 position, the double bond in the 3 position is supposed to be E, and that is what we have here. Okay. This here, the lowest group are trans to each other, so that is E. And then in the 5 position, we also have Z. That means the lowest group are on the same side, which means that this hydrogen and this methyl on the same side of the double bond. Okay, and that completes the structure that we are supposed to give. Of course, tetraene means that you have double bonds in position 1, 3, 5, and 7. Now, if that is clear to you, give me a happy face. Okay, very good. Excellent, excellent. Okay, so we are moving right along. Let's go to question number. I told you we don't need to worry about question number 8, so let's go to question number 9. Okay, question number 9. Kiara Wallace, can you go ahead and read this question for us?
Determine shall have for full credit the absolute configuration of the priority carbons in the following molecule.
Okay, thank you, and very good. Okay, so what they want you to do here, this is a stereochemistry question, to determine the absolute configurations of the chirality carbons in the following molecules. Of course, as you can see here, this is a chirality carbon here, and this is another chirality carbon. Okay, to do this, this is what I always wanted to do. Write out this molecule here in what I call a Fisher projection formula. Okay, write this out in a Fisher projection so that you see this chirality carbon here, the groups that are attached to it, will be seen in that Fisher projection formula. Okay. Now, the way I want to do this, by the way, you could do this any way you want. Imagine that I am standing right here. This is my face facing this carbon here. Okay. Imagine I'm standing between the hydrogen and the isopropyl group. Okay, this is hydrogen here, this is isopropyl group. Imagine that my left hand is right here and my right hand is here. Okay, this is my right hand my left hand. So that gives you a reference to where I am standing. Okay, let us now draw the Fisher projection. Okay, the central carbon is this here. Okay, I want you guys to tell me what group or atom is on my right. What group or atom is on my right? Okay. What group or atom is on my right? Okay, hydrogen. Very good. Hydrogen is on my right. So therefore, the isopropyl group is on my left. Okay, that means that this group here, the NH2 group, is above my chest, and this group here is below my chest. Okay, now let us assign the absolute configuration. Before we do that, we need to assign the priority based on the Kern-Ingold pre-log sequence rule. So this would be A, priority A, nitrogen, and priority B will be this group right here, and priority C will be this here, and priority D is hydrogen right here. Okay, so now I want to make could I repeat what I said? Okay, what I was saying was I am standing right here, right? And this is my right hand. Just to give you a reference to where I am standing, and this is my left hand. Okay. Why is an Na2 priority A? Because if you look at your periodic table, nitrogen has a greater atomic number than carbon atom. Okay. Okay. Anyway, so let us make our motion from A to B to C. Ignore group D. Completely ignore group D. So we go from A to B to C. Okay. What is that motion? What does that motion tell us? What does that motion tell us? That motion is clockwise motion. Right. Very good. So therefore, we would expect that this will be R. However, what do we need to do here? However, because the group of lowest priority, which is hydrogen here, is coming at you, keep in mind in your Fisher projection, the horizontal group, you assume the horizontal groups are coming at you. Okay, so because that hydrogen is coming at you, you have to switch. So this is actually S. So therefore, the absolute configuration here is S. Okay? Now let us do the same thing here. Let us do the same thing here. Okay? I am going to position myself between this group here and this group here. So imagine that I'm standing right here. This is my face looking directly at this carbon. I'm looking at this carbon. So I am standing. I want to position myself. Okay. My legs. Okay, this is my left hand, and this is my right hand. Okay, just to give you a reference as to where I am standing and looking at this carbon here. This is my right hand. Okay, so therefore, I will ask you, okay, this carbon here, this is this carbon right here. Okay, what will be on my right? What group will be on my right? What group will be on my right? NH2, very good. The amino group, NH2. Therefore, on my left will be your ester group. Okay, what group will be above my chest? The isopropyl group, very good. And therefore, below me, below my chest will be the hydrogen. Okay, so let us make the priority assignment and then assign the absolute configuration. Okay, nitrogen, this is A. This group here, therefore, will be B. And the isopropyl group will be C. And the hydrogen will be D. So we make our motion from A to B to C. We ignore group D, A to B to C. Okay, so what is that motion again? What is that motion again? Okay, clockwise, which means that it is R. Okay, do we need to make a switch? No, we don't need to switch because the group of lowest priority, D, in this case hydrogen, is going away from us. It's in the vertical position of a Fisher projection. Keep in mind those groups or atoms in the vertical position of a Fisher projection, they are assumed to be going away from us, okay? So therefore, this is actually, it remains R. So therefore, this is R. Okay, now let me ask you this. Let us call this compound A and compound B. What is the stereochemical relationship between compound A and B? What will be the stereochemical relationship between compound A and B? Or I may simply just ask you, what is the relationship between A and B? Okay? Enantiomers, exactly. They are enantiomers. They are enantiomers. They are enantiomers because both compound A and B are mirror images that do not superimpose on each other. Mirror images that do not superimpose on each other. Okay? Okay? Now, if you look at the way we draw these molecules here, you will say, well, you don't see that they are mirror images. Yes, they are mirror images. It's just the way we draw them look like they are different. But if you do the absolute configuration, you see this is R and this is S. And then you look at this molecule here. Both of them have the same molecular formula. Both of them also have the same attachment of the atoms. So therefore, the only difference between them is the orientation of those atoms in space. In this case, this carbon is RS, absolute configuration, and this carbon is R, absolute configuration. Okay, so let us go to the next question, unless you have a question here. Okay, it's almost 9 o'clock, so we'll try to leave here by 9:15. Let's see. Okay. Okay, number 10, question number 10. Okay, Brittany Galloway, can you go ahead and read this question for us?
Using the formula C4H10O2 in Fisher projections, draw two molecules that are configurational diastereomers of each other.
Okay, very good, and thank you. Okay, so what you have here, we have this molecular formula here, and they tell us to write Fisher projection of two molecules that are configurational diastereomers. Okay, let me tell you right away. If I was you, the first thing I would do here, I would determine the index of hydrogen deficiency here to see whether there is a double bond or ring in this molecule. Using this formula, index of hydrogen deficiency, carbon minus number of hydrogen divided by 2 minus halogen divided by 2 plus nitrogen divided by 2 plus 1. Now, if we use this here, let us see. Carbon is 4, hydrogen is 10, so that is minus 5. There is no halogen, so we don't need to worry about that. There is no nitrogen, so we don't need to worry about that. So plus 1, if you look at it, this is 0. So what this tells you, there is no double bond or ring in this molecule. Okay, now that we know that, let us do what they tell us to do. Write two molecules that are configurational diastereomers. In other words, you must write two molecules that have at least 2 chirality carbons. You must have two molecules that have at least 2 chirality carbons. So I will say, okay, and you only have 4 carbon atoms here. Following all of the rules of valence and octet rule, okay, I say this is a possibility. 1, 2, 3, 4. Okay, you have 4 carbon atoms. How many hydrogen? 3, 6, 8, 10. So we have all of the hydrogen, oxygen. We have all of the oxygen. So this molecule will work just fine. And then we see here, we have 2 chirality carbons here, this and this. Okay? So we want configurational diastereomers. The question is, what are configurational diastereomers? Configurational diastereomers are stereoisomers that are non-mirror images. Let me write that down. Configurational diastereomers are stereoisomers containing, they must containing at least 2 chirality centers, at least 2 chirality centers, comma, and are not mirror images. Okay, so given that definition, somebody say if there was an if there was somebody's asking here if the IAD was 1 or 2, that tells you you have a double bond or a ring. Okay. Anyway, so here let us write the other possibility. Okay, let us call this compound A and compound B. Now, compound A and B will be configurational diastereomers. You notice here, These are stereoisomers, both of them. They have the same molecular formula. They have the same attachment of atoms. They have they have 2 chirality carbons each, but they are not mirror images. Okay, so that satisfies the question here. If you understand that, can you go to the? Can you give me a happy face? Okay, very good, very good. Okay, 11. Okay, Robin Onoha, can you read this question for us?
Write the IUPAC name for the following compounds, including EZ stereochemistry.
Okay, very good. And thank you. Okay, let me ask you this. What is the longest carbon chain in this molecule that we are going to use for the base name? Okay. Longest carbon, what is the longest carbon chain? Okay, 12. Okay, let us do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Very good. So therefore, that means we have branches, a methyl branch in position 3, another methyl branch in position 7, another methyl branch in position 11. And in this molecule, we have 1, 2, 3, 4. 4 double bonds. Okay? So the base name, therefore, since we have 12 carbon here, the base name will be derived from decane. Okay? So what we are going to do here, we are going to remove the Ne suffix and replace with the tetraene suffix later. Okay. So we have that. Now, let us now do we know that we don't need to worry about stereochemistry for the double bond in 1. Okay, let me ask you this. What is the stereochemistry of this double bond between 3 and 4? Is it E or Z? Anybody? E or Z? Okay, that is E. That is correct. E is correct. It is E. Okay, how about the double bond between 6 and 7? Is it E or Z? Okay, we have this here, and then we have this here. Okay, very good. That is also E. Okay, so we don't need to worry about the double bond in position number 10. So let us go ahead and give the name for this. So we say 3E, comma, 6E. Okay. Then we give the position of the branches. 3, 7, 11, tri, methyl. Now we give the position of the double bonds. 1, 3, 6, and 10. 1, 3, 6, and 10. Then we now have dodeca. We remove the Ne and we replace with tetra. Okay, and that is the name for that molecule. Okay, so let us go to the next one. Go to question number 12. Oh, I told you we don't have to do number 12. Okay, so we go to 13. Okay. This is the question. Somebody is asking, why didn't we do Okay, if you can hear me, give me a happy face. Okay. I think I lost my internet very briefly there. Okay, yeah, I think I lost my internet for a second there. Okay. Somebody was asking, where was the question? How come we did not do the stereochemistry for the last one? How come we did not do the stereochemistry? Okay. Somebody say, how come we did not do the stereochemistry for 1 and 10? You cannot do stereochemistry for a carbon-carbon double bond if any of the carbon-carbon double bond is attached to the same atom or the same group. Here you have hydrogen here, and on this here you have a methyl here. You have a methyl here. You also have another methyl here. So we cannot do stereochemistry for this or for this. Okay. Okay. This is the question of the day. Muhammad, can you go ahead and read this for us? Muhammad Fahad. Is Muhammad there? Okay, maybe Muhammad is having problem with his mic. Let me see. Okay, Brittany Galloway, can you go ahead and read question 13 for us?
Compound A, C10H16, reacts with dilute acid to give compound B, C10H18O. Compound A also reacts with KMnO4 to give a non-symmetrical compound C, C10H16O2. Write structures for A, B, and C.
Okay, thank you. Very good. Now, this is what we call a roadmap question. Roadmap question. You will be getting questions like this as we move on in this semester. Now, any one of you, if you wish to get a B or an A in this class, this kind of question you need to be able to do, because this question here requires a lot of thinking. Okay, let us start here. We have compound A. The molecular formula is C10H16. So this is another case in which you want to use your index of hydrogen deficiency, IHD, equals to carbon minus H/2 minus halogen over 2 plus nitrogen over 2 plus 1. Here, carbon is 10. Okay, hydrogen, okay, 16 divided by 2, that is 8. No halogen here, no nitrogen, so that is plus 1. So therefore, the index of hydrogen deficiency is 3. Okay, we now know that. We know the index of hydrogen deficiency is 3. What does that mean? This molecule will have either double bonds, or rings, or even triple bond. Okay, now, they now tell you compound A reacts with dilute acid, which will be essentially saying water with some kind of acid catalyst, okay, say dilute acid, to give compound B, okay, and compound B has a molecular formula of C10H18 with oxygen. Now, if you work out the index of hydrogen deficiency, let me write this here, IHD for compound A is 3. If you work out the index of hydrogen deficiency for compound B, you will find out that it's only 2. Okay? Now, that is after the reaction with this here. Then the question you also want to know is, what does this reagent do? At this time, you guys should know what this reagent does. What it does is to add hydrogen and OH across a carbon-carbon double bond. This is what we call hydration. Okay, so therefore we are forming an alcohol. Okay, now, so if we react this with this, and we only do, we see end up with 2 index of hydrogen deficiency, what that is telling us is that compound A must have 1 double bond Okay, compound A must have 1 double bond and 2 rings. Because if we have more than 1 double bond, this reagent here will react with all of those double bonds. Okay, but what we have here, it reacts with only the double bond that was there to form this compound. So far, so good. Then it says, continue to tell us, compound A, which is this here, reacts with potassium permanganate. That's why I told you that this question requires some thinking. Okay, reacts with potassium permanganate to give compound C. And what is the formula for compound C? It says C10, H16, and 2 oxygen. Okay? So what has happened here? The next question you want to ask yourself is, let me ask you this. What does this reagent do? Can anybody tell me? Potassium permanganate. What does it do? That is very important for you to know. What does it do? It cleaves, exactly. It cleaves to do what? To form ketone? No, no aldehyde. No aldehyde. No, don't get that wrong. For carboxylic acid and ketone, exactly. It forms to form either carboxylic acid or ketone. Now, it forms carboxylic acid or ketone depending on what, if you have hydrogen attached to any of the carbon, it becomes carboxylic acid. If you have no hydrogen, it becomes a ketone. Okay, so what do we have here? We already told you compound A has a double bond, right? Compound A has a double bond, and then it reacts with this to form compound C. And how many oxygen do we have here? We only have 2 oxygen. If it cleaves to form a carboxylic acid, we get it, right? In that case, we should have 4 oxygen. So therefore, that cannot be the case. We don't have carboxylic acid here. If it cleaves to form carboxylic acid and a ketone, we should have at least 3 oxygen here, but we don't have 3 oxygen. So this is out. And you notice why I told you, you need some thinking here. Now, we ruled out those possibilities. So therefore, what would be the possibilities here? The possibilities is that you're forming 2 ketones. You're forming 2 ketones, okay? Because you only have 2 oxygen here. Okay, now it says, whatever this compound C is non-symmetrical, okay? Now, let us look at the possibilities. Let us now look at the possibilities, okay? Keep in mind, we told you that compound A must have 2 rings. Okay, we formula is C10. Okay, this is one possibility. We must have 2 rings and 1 ring, and 1 double bond. Okay? Supposing we have the double bond here. Okay? Do you know why I put the double bond here? This is the only place I could put the double bond that will get two ketones. Because if I place the double bond here, and the potassium permanganate reacts with that, we get carboxylic acid. So this is the only place I could put the double bond to get two ketones. So if you do that, this is what you get with potassium permanganate. Then you get these two ketones here. But they told us that compound C is non-symmetrical. Okay? So it cannot be this, because this will give you symmetrical ketones. So it cannot be this. So therefore, it has to be this. Whatever you give me cannot be a symmetrical compound. Double bond is here. And when you cleave this, with potassium permanganate, you cleave it right here, you get this. A ketone here and a ketone here. And this is compound C. Okay? So this question does require that you think. So this is the kind of question I will put in an exam to distinguish between those who want an A and a B. Okay? If you want an A or B, you must be able to do this kind of question. Because what does it do? It puts together all of the knowledge that you're supposed to know in terms of knowing your reagents, knowing what the reagents do, and then it forces you to think critically. Okay? Is there any question on this? Okay, so let us go to the next one. I think we are almost 5 more minutes and then we call it a day. Okay. Number 14. Okay. Okay, Matake Hutchinson, can you read 14 for us?
Write the Fisher projection structure for an optically active carboxylic acid with the formula C5H10O2.
Okay, thank you. Very good. This should be fairly simple. Okay, just write Fisher projection of any optically active carboxylic acid using this formula here. So, like I said, this should be fairly simple. Any structure will do here as long as it will be optically active. And the key here is that since you only have 5 carbon atoms, you must at least have 1 chirality carbon. Okay, so I will say this. So how many carbon do we have here? 1, 2, 3, 4, 5. How many hydrogens? You have 5 hydrogens here. That is 9. That is 10. Okay, and 2 oxygens. So this molecule here will meet the requirement of this particular problem. This has a chirality carbon right here. And this molecule here will be optically active. Somebody asked a question. Somebody said, what was compound B? I'm sorry about that. Yeah, thank you for that. I gave you compound C. Did not. Okay, compound B will be, thank you for reminding me of that. Compound B will be this here. Keep in mind, this reagent here, what does it do with the double bond? Okay, so you are going to add water across the carbon-carbon double bond. Okay, So this will be this here. Okay, that is compound B. Okay. Let's go to, I think we're almost through. We've done that already. Okay. Okay. This one here, okay? This should be fairly easy to do. For this question here, I want you to ignore this part of this question. Ignore this. Ignore this. Okay? Okay. Supposing I tell you that compound B has a formula C10 H20, right? And it reacts ozonolysis. That's what we have here. Step 1, ozone. Step 2, zinc in dilute acid. Okay? And I say, what is compound B? Okay, that is what this question is asking you. If you do your index of hydrogen deficiency, IHD, for this molecule here, you will find that it is 1. The index of hydrogen deficiency is 1. So therefore, what does that mean? What does that mean? Okay, it means that you have a double bond or a ring. Now they tell you compound B reacts with ozone to give only this here. Okay, so what would that tell you? What would that tell you? That compound B must be a symmetrical molecule. Keep in mind, what does this reagent do? It will cleave a carbon-carbon double bond to give you a ketone or aldehyde. So in this case, since we are only getting this, I will say compound B is this here. That is compound B. Because if you cleave this, if you react this with ozonolysis, okay, what do? You cleave right here. Okay, you only get this compound here. Okay? That is a fairly simple one. Okay, that is 15, 16. Okay. Okay, 16. We have 2 more questions. Let's do 16 and 18, and then we call it a day. Okay. Number 16. Let me see here. Erin Walters, can you read this for us?
Compound Y gives the following products upon oxidative cleavage with KMnO4. Give the structure for compound Y.
Okay, thank you. Now, you see, most of these questions here, I keep going back to what I keep telling you. You must know what this reagent do. So this is a question of what does this reagent do? Okay, potassium permanganate. Okay, we say compound Y. Okay, potassium permanganate. Okay, what does it do? It will cleave a carbon-carbon double bond to give you what? Can somebody tell me? What does it do? Cleave a carbon-carbon double bond to give you what? Ketone and carboxylic acid. Excellent. So therefore, we say compound Y gives you this in one step. This is a ketone. This is a carboxylic acid. So what does that tell you? Let me number this. Let us say this is carbon 1, 2, 3, 4, 5, 6, 7, and 8. Okay? Now, what does that tell you about this compound Y? Which carbons are you going to join? Can you tell me? which carbons are you going to join to form the carbon-carbon double bond? Which carbon are you going to join to form the carbon-carbon? 6 and, no, you got to join 2 carbons. 6 and what? To form a carbon-carbon double bond. 6 is correct. 6 is correct, okay. See, where did the carbon, see, okay, we have carboxylic acid on carbon 1, right? You told us that to cleave the carbon-carbon double bond to form ketone or carboxylic acid. We have carboxylic acid on carbon 1 and ketone on carbon 6. Exactly. So that means you have to join carbon 1 and 6. Okay, so let us do that. If I do that, okay, imagine that I have a double bond between carbon 1 and 6. Okay, let me count the number of carbon here. 1, 2, 3, 4, 5, 6. So I will have a 6-member ring. These are those questions that require that you do think critically. Okay, we have a carbon-carbon double bond, and then we have a CH2, a CH3. Let me number those carbons for you again. So therefore, this will be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So when we react this with potassium permanganate, what does it do? It will cleave. It will cleave this. Okay. Don't forget this carbon 1 here has an hydrogen here. So it will cleave this so that carbon 1 is now this here, and carbon 6 is now this ketone. Okay. If you see that, give me a happy face. Okay, very good. Okay, let us do the last question, and then we call it a day. It's almost 9:30. Okay, I know you guys need to go home and relax for the rest of the evening. Okay, I told you don't worry about 17. Okay, 18. Very good. This is a good one to end the day. Okay. Let me see here. Who can I call on here? Danuchika Gering, can you read number 18 for us?
Starting with the alkene shown below, write the structure for the products that will form upon reaction with each of the following reagents. You must indicate stereochemistry when appropriate. If there is no reaction, indicate NR.
Okay, very good, and thank you. Somebody is saying here, how can you have a double bond between carbon 1 and 6? Okay, before I come to this question, let me go back and answer that question. Okay, except because how will you name this? Okay, how will you name this molecule? The question is, how will you name this molecule? Okay, can anybody name this molecule for us? Anybody wants to try and name this molecule? Okay, I will give the base name is cyclohexene. Okay, so that would be ethyl cyclohexene. Okay, so now let us. Somebody was asking how will you name that compound? Okay. Okay, Masha K. Hutchinson, go ahead. Masha, can you ask your question?
For that same molecule, could you have made it a symmetrical molecule?
Can I make it what? Say that again.
Could you make that into a symmetrical molecule? As in compound Y being the symmetrical molecule of the structure right there?
Make it a symmetrical molecule. No, you cannot make this a symmetrical molecule because compound Y is not symmetrical. See, this is compound Y. When you clip this here, you get this compound here. So you cannot make it. You cannot make it a symmetrical molecule.
No.
Mm-hmm.
I was asking if you could make compound Y itself symmetrical.
Can you make it symmetrical?
Yes.
No, you cannot make it symmetrical. Because the AT group is attached to this carbon here. Okay, this is a 6-member ring. You have a 6-member ring here. Okay, you cannot make it symmetrical.
Not the ring.
Okay, Kiara.
Not that ring right there. For instance, the structure that is given there, the product that is given.
Oh, the product that is given. Oh, you want me to draw it in a way that would look like.
It's two.
Okay, I see. Okay.
Yes.
Okay. Okay, I see what you're saying. Okay, let me do. Okay, if I clip this here, you want me to make it obvious.
And then if you
okay.
have like a molecule where the O is, you have the C there.
I hope that is what you want me to draw, but you cannot make this symmetrical. Anyway, let us move on here. Okay? Okay. Okay, so let us look at this here, 18, and I believe, was it Danushika that read that question for us? Thank you. Okay, now what do they have here? They want us to start with this here, and use any one of these reagents and give the product. Okay, let me tell you right away, if you have a carbon-carbon double bond and you have potassium hydroxide or sodium hydroxide, this reagent does not react with a carbon-carbon double bond, at least based on your knowledge of organic chemistry at this point. So I will say no reaction, okay, for this. Okay, then the next one, B, potassium permanganate. Okay, potassium permanganate. What will be the product? Okay, what does this potassium permanganate do? Once again, it comes back to knowing what the reagents will do. What will it do? It will cleave this carbon-carbon double bond so that this carbon becomes a carboxyl group and this carbon becomes a ketone, okay? Keep in mind you have hydrogen here, so therefore the product that you will get will be this. Okay, and then this here, and this is here. Okay, so that is the product you get with this. How about C, reagent C? Okay, so we get carboxylic acid here on this carbon here, which is this carbon, and a ketone here, which is this carbon. So carbon C, reagent C. If you do this, hydrogen and palladium. Okay, what does that do? Okay, once again, you need to know what this reagent do. It will add to add two hydrogen atoms across the carbon-carbon double bond. So therefore, you get this. And this is a cis addition. Okay, the metal is here. And this one is here. Okay. Okay, notice this reagent here. What does it do? Oh, I'm sorry. It will add two hydrogen atoms across the carbon-carbon double bond. Okay? And that's what you see here. Okay? Two hydrogen atoms. Okay, about this here, okay, ignore this. This reagent here, I have not shown you what this reagent, we have not done this in class here. So ignore, if you see this kind of reagent at this point, ignore this. Okay, so let us go to E. What does it do? What does this reagent do? Anybody? What does this reagent do? Okay. Like I say, you guys need to know what this reagent do. If you don't, you'll be in trouble. Okay. What this reagent do, add OH is very good, excellent. And it adds the OHs in a mechanical fashion. Okay, so we have hydrogen here. Okay, so now we have hydrogen goes here. Okay. Okay, so it has this hydrogen and this OH in a mechanical fashion. Okay. Okay, the hydrogen goes to the carbon that contains more hydrogen, and the OH goes to the carbon that contains less hydrogen. Okay, so far so good. I'm sorry, that is E. Let me go ahead and write that. Okay, now let us do F. Let us do F. What does this reagent do? Anybody? What does that reagent do? What does that reagent do? Cis addition of what? Two OH. Excellent, excellent. Once you know what those reagents do, I guarantee you, you will not have any problem. So now you will have this. You have a cis addition, you have OHs. Okay, of course, you know the hydrogen was here before. And the methyl that was here before is still here. You notice here, this OH and this OH, they are added across the carbon-carbon double bond in such a fashion that both of those are cis to each other on the same side of the ring. Okay, very good. And that is the osmium tetroxide followed by sodium hydrogen sulfide. Okay, about G. What does G do? What does this reagent do? What does that reagent do? Anybody? What does it do? This reagent here. Add OH and what else? Add OH and what else? Okay, OH and hydrogen, and it's an anti-mechanical addition. Exactly. That is an anti-mechanical addition. Okay, so you have step 1, borane, and step 2, hydrogen peroxide in basic medium, So what that reagent does is to add hydrogen and OH across the carbon-carbon double bond. Okay. Okay, and therefore we have this here, anti-Markovnikov of addition, so the OH will come here. And then what it also does, it is a cis addition. It adds the hydrogen and the OH. It's a cis addition. Okay. Okay, it's anti-Markovnikov reagent. It is also a cis addition reagent. In other words, the OH and the hydrogen will be added on the same side of the molecule. Do not forget that this other hydrogen was here before. This here. Okay? Okay, now this question H, this here, don't worry about this yet. We have not done that reagent yet. How about this one here? What does this reagent do? Anybody? Okay, anybody has an idea? Okay, cleave. What does it cleave to give? You need to know exactly what it does. What does it cleave to give? Ketones or aldehyde. Excellent. Ketone or aldehyde. Okay. Okay, this part of the molecule, this carbon here, become an aldehyde because you have hydrogen attached to it. This is ozonolysis. This carbon here becomes the carbon of an aldehyde because it contains hydrogen, and this carbon becomes the carbon of a ketone. Okay, so therefore, okay, so we have aldehyde. Let me have this here. And this other carbon here. That is the carbon of the ketone, this one here, right here. Okay? Okay, about this one here, sulfuric acid. Actually, they should also add water here. What does this reagent do? What does this reagent do? Okay, what does this reagent do? You guys need to know your reagent. Exactly. Add hydrogen and water. Excellent. Excellent. So that will do 1, 2, 3, 4, 5. Okay, so we have this here. So this reagent will add hydrogen and water, and it is a Markovnikov addition. So therefore, the hydrogen, keep in mind, hydrogen was here before, so it will add this hydrogen, and it will now also add water. So it is adding this here and this here. It is a Markovnikov addition of water. Okay. How about this here? K. What does this do? What does that reagent do? Chlorine. What does that reagent do? What will it do? Anybody has an idea? What would that reagent do? This reagent, chlorine, what will it do? Transaddition of, okay, transaddition of chlorine, exactly. To add chlorine. One chlorine here, another chlorine. This is transaddition. The same thing if you have bromine, to get a trans addition. Of course, the methyl that was here before and the hydrogen that was here before is here. Okay, in this case, the chlorine and this chlorine are added to the carbon-carbon double bond, and this is a trans addition reaction. So that means that this reagent here, okay, is a trans addition reagent. Okay, and finally, this here. Okay, what does this reagent do? Okay, M-chloroperbenzoic acid. Okay. Oh, okay. Followed by hydronium ion. Okay. Keep in mind the M-chloroperbenzoic acid by itself will give epoxide. Then if you follow that up with the acid, what does it give you? What does it give you? What does it give you? This reagent here, this combination right here, what does it do? What it does is to add, this is hydroxylation. In other words, you are going to add hydroxylation. In other words, you are going to add two OH groups across the carbon-carbon double bond in a trans addition. Okay? That's what that reagent will do. Okay, so we have this here, this here, this here, this here. Okay, so we have this is here, this is here. So now we have OH, another OH. I'm sorry, this is the opposite of the osmium tetroxide. The osmium are two OHs in a cis addition fashion, but this one here will add two OHs trans to each other. Keep in mind you had the hydrogen here before, still here, and then the methyl that was here is still here. Okay, folks, we have spent a lot of time tonight. Unless you have additional questions, we have come to the end of today's session. And I hope you enjoyed the rest of your evening. I will try as much as possible to post this material either tonight before I leave my office or early tomorrow morning, and I will let you know. Once we finish the session today, when we finish the session, I will stay online for another 5 minutes, additional 5 minutes, just in case some of you want to ask me additional questions offline. Okay? So let me stop the recording. So folks, enjoy the rest.